Welcome to qnawire.
So we're asked to repeat the previous problem by replacing the open feed water heater with the closed feed water heater. And we want to assume, what does it say here? Feed water leaves the heater at the condensation temperature of the extracted steam, and the extracted steam leaves the heater at a saturated liquid and is pumped to the line carrying the feed water. All right, so we come up here. From the pump, we pump it up. Again, we're at 6 megapascals at the high side. At this bleed pressure, we have 400 kilopascals, and down here at the low side, in the condenser pressure, we have 20 kilopascals. So we bleed some off here, and then we basically pump it up to this pressure here, and then we pump it. We have this pumped up to that pressure also. And then we have, let's see, heat transfer in this region. And then we have everything going off basically back to the turbine. So again, this is a closed system. So we just have heat transfer in the feed water heater, and we don't have mixing. We have mixing down later on. Now, let's see here. What we have then is a lot of the stuff is the same, but now we have two pumps. So if we look back here, we had two pumps too here, but we one pump was kind of a little work, and the other one was here. So now we have a pump pumping this one and pumping up to here. So we're going to actually put in quite a bit more work into the pumps, but again, that's always a small fraction of the total turbine work that we get out. So the work we're going to put into the first pump is about 6.1 kilojoules per kilogram, and so that gives us an enthalpy at 2 of about 258 kilojoules per kilogram. And likewise, we can get the enthalpy and the specific volume at 3, which then gives us the specific work from 3 to 9 is very, very similar because, again, we're pumping from here to here doesn't require a lot. So going from here to here and from here to here is much the same. So, and then we can get the enthalpy at 9. Okay, so that's up here. That's where we've pumped the bleed steam off up. And so then well, it was steam, but now it is liquid. So now we have the enthalpy at 9, and the enthalpy at 4 and at 8 are the same as at 9. So we have, let's see here. Yeah, okay. So then we have the enthalpy at 5 we can get because we know the pressure, and I think I didn't write the temperature again in here. T5 was, what did we have? Find it was 450. And then again, we know that S5 equals S6 equals S7, and S1 equals S2, and S9 equals S3 because of the isentropic pump and turbine. So let's see here. Then we have, we can get the entropy at 5, which is the same as entropy at 6 and 7. So now at 6, we have entropy and pressure, so we can get quality factor and enthalpy. At 7, we have pressure and entropy, so we can get quality factor and enthalpy. And then we can look at the energy in and the energy out let's see here, what are we looking at here? We're looking at basically in this region here. Hold on a sec. Let me make my notes and just make sure I'm saying the right thing here. Let's see here. There is. Hey, I thought. Let's see here. There we go. Scroll back here to my notes. Let's see here. We are looking at the so we know in the state the feed water heater basically, right? So we're looking at the feed water heater, or the steam extracted, the fraction of the steam extracted, the steady flow energy balance equation applied to the feed water heater. Yep. So this is the feed water heater. Again, we have kind of a cross flow system. So we have enthalpy here and here, and then the enthalpy here and here. Basically, this is where they're crossing. In the feed water heater. So again, we know then we can get, if we divide through by M5, M.5, which is the same as M. Let's see here. Yeah, which is the same. Let's see here. Again, we have mass conservation too. So M.5 is the flow through the turbine here. And so through here, we have 1 minus y. Oh, sorry. We have y. And then through the other region, we have 1 minus y. So that's where we get these. And again, we have mass conservation in the, no, we don't need we don't have mass conservation in the, well, we have mass conservation in the two pipes through the heater, but not in everything. So anyway, we can get this expression here for y, which is the ratio of the mass flow rate through the, let's see here, through the bleed line divided by the mass flow rate through the turbine. And that winds up being 0.1, about 0.15, or about 15% of what we're taking off here. So that would be, coming off of here, we're taking about 15% of the steam out by mass. And so then we can get the heat transfer in, which is simply the heat transfer from 5 minus 4. So that's where it's going into the boiler. So after we have everything mixed, and so that we get that value here, and then the heat transfer out, we can look at the again, the heat transfer out in the condenser is here, happens over this region. And so again, we don't have the full flow flowing through there. We just have 1 minus y because we subtracted y here. So we have 1 minus y here. And so we get a heat transfer out, which then the difference of these things is the net work out, and then we can get the efficiency. And that winds up being 37.8%. And in the previous problem, we had 37.8%. Now, it's slightly different because you can see here, this is slightly different. Each of these values are very slightly different. So if we kept another decimal point there, we might see a difference in these efficiencies. But in this case, they're very, very similar.